Hello, I'm going to be presenting the demonstration of non-anthropogenic arsenic and the non-anthropogenic standard selection for the Yellowstone River. This project was completed by the Water Quality Standards section of the Water Quality Planning Bureau of the Montana Department of Environmental Quality. If you have any questions, please contact Mila Kelly at 406-444-3639 or email her at mkelly2@mt.gov. The presentation today will go over a little bit of history about the non-anthropogenic standard selection. It is a two-step process that has been developed. The first process has been acronymed the DAWN, and that's the demonstration of non-anthropogenic. And the second step is the actual NASS, or the non-anthropogenic standard selection. And then we'll go over some conclusions. Okay, a little bit of history. This is this process, and the arsenic site-specific standards for the Yellowstone River is a spinoff of SB 325 legislation. And the process was actually first completed for the Madison River, DAWN, and NASS, and that draft documentation is available on the SB 325 workshop or website. And the DAWN and the NASS process have been reviewed by the SB 325 work group and EPA as part of the DAWN and NASS for the Madison River. And the DAWN and NASS for the Madison River were developed, and these same processes were used to develop the Yellowstone River arsenic DAWN and NASS. And again, these are preliminary results for the Yellowstone River DAWN and NASS, and they are subject to change as internal and external review is completed, and the documentation will be released in 2018. So let's go over the demonstration of non-anthropogenic first for the Yellowstone River. Okay, so it's quite the process, and we developed this process in this flow chart when we were doing the Madison River DAWN, and it is the same exact process that we use for the Yellowstone River DAWN. And so the first step in the demonstration of non-anthropogenic is to define the hydrologic region. So what is the actual area that we're dealing with? And then once we define that area, or the area that we're going to model, we'll compile all data, existing data. It's going to be ambient water quality data and any potential anthropogenic sources. The potential anthropogenic sources data that we're looking at is point source, so MPDES permits, any other type of point sources that we can compile, groundwater sources, runoff, and tributaries to the Yellowstone River also have a anthropogenic component. And then we look at all the data we compiled and ask the question, is there sufficient data? And we did develop a metric to actually determine if we have sufficient data, and that actually is outlined in the documentation. And if in the case of the Yellowstone River, there wasn't sufficient data, so we had to go out and collect more data in order to complete the mass balance approach. So once we have enough data, we move on to the mass balance approach, and the mass balance approach, once once that's completed, we consult with EPA, DEQ, the SB 325 work group, other stakeholders to get their input on the way we went about doing this demonstration of non-anthropogenic. And then when we're all complete, we ask the question, was this process defensible and valid? And we do believe that it is valid. We do have a valid DAWN, and we can move on to the next step, which is non-anthropogenic standard selection. Now, I'll go over the NASS in just a little bit, but let's just give some examples on this DAWN process. For more detailed explanation, the documentation will spell out all this entire process, but I'll just give you some summary highlight points. Okay, so in the first step of the process, defining the hydrologic region, this is the region. It's a rather large region we're looking at quite a few Huck 8 and the Yellowstone River from the Wyoming border to the confluence with the Bighorn River. Okay, the hydrologic segments. We divided the Yellowstone River into 5 hydrologic segments, and these divisions are basically based off of hydrologic divides, and also where there was a measurable difference in concentration of arsenic after that hydrologic divide. So, for instance, when we're looking at the Clark Fork of Yellowstone River at Laurel, this is where the Clark Fork of Yellowstone River comes into the Yellowstone River, and then you do see a measurable difference in concentration down gradient of that confluence. Okay, and this is just showing this in a graphic or a picture to show you those different hydrologic segments. Again, there were 5 segments that we modeled. Okay, so, and as I said before, there was a lot of data compilation. We looked at existing data, DEQ data, EPA data, USGS data, other various groups throughout Montana that collect data, and then went out and then collected additional data for the model. Okay, these are some of the permitted point sources that we looked at. As you can tell by this figure, the majority of point sources are in the Yellowstone, or I'm sorry, in the Big Sky, or sorry, in the Billings area. And we also looked at Wyoming because there are some the hydrologic units in the Wyoming area do spill into the Yellowstone River. We didn't find anything that of substantial value that would contribute anthropogenic arsenic to the model. So they are included on this map, but they weren't big red flags of arsenic. So it wasn't, you know, a big deal. But you can see that there are quite a few stormwater permits, individual permits, general permits throughout the model. And we did look into every one of them, even if they didn't include any type of arsenic modeling in their permits. Okay, these are the permits that permitted point sources that were considered significant and draining into the Yellowstone River, so we included them as point sources in the model. What you're looking at is 2 points in time, June and December, and a lot of these permittees only have to sample twice a year, so we decided to use June as a high flow example and then December as a low flow example to see the 2 different values. And what you can basically, you know, from this graph and take away from this is that in June, only 0.145% of the arsenic in the Yellowstone River at Billings is actually from permitted point sources. And in December, low flow, where you do have less water, less dilution, it is a little more significant. It's 0.856, but it's still less than 1% of the total arsenic in the river. Okay, and we also looked at tributary contribution. Again, tributaries have the potential to add anthropogenic as well as non-anthropogenic arsenic to the Yellowstone River, and this is quite a large area that we looked at. Okay, and all this feeds into, again, this is a summary view. There's a lot more detail that goes into this model, and that is in the documentation. We compiled all this information that we gathered into a mass balance. And a mass balance approach is basically taking concentration, timesing it by a flow condition, and then getting what's called the mass load. So we can compare all this information apples to apples, and we convert everything into a mass load. Okay, the mass load equation for the Yellowstone River is the total arsenic load, and that is the ambient load of arsenic that we're actually measuring in the river. And then that ambient load of arsenic in the Yellowstone River includes the initial load that is coming from Yellowstone National Park, any point source loads, and we went over that, permitted or non-permitted, groundwater contribution, and again, groundwater contribution also has an anthropogenic and non-anthropogenic input. Tributary also has non-anthropogenic and anthropogenic, and then runoff, which also has a non-anthropogenic and anthropogenic component. And that is the total arsenic load in the Yellowstone River. Okay, so the fast forwarding to the yearly, so we put everything into the mass balance, and we were able to create a yearly mass balance for each 1, 2, 3, 4, 5 segments of the Yellowstone River. And the first column is the total arsenic load, which is, again, what I told you is the ambient arsenic load in the Yellowstone River. And what's included in that is any source loads, which would be, for this case, the Yellowstone River, we did have point source loads, and we did have groundwater loads that were anthropogenic. And then there's a anthropogenic runoff component that's added into that. And then we do a running total of all those anthropogenic loads because it's cumulative over the entire length of the model. So all these loads add up until we get to the end of the model. And what we can subtract all this out from the total arsenic load, and we get the median non-anthropogenic load, or the non-anthropogenic condition, and that's the final column. And this is the numbers that go into the when we calculate or select the non-anthropogenic standard. So these are the numbers we'll be using in the NASS. We're not using an ambient load, we're using a non-anthropogenic load. Okay, so the mass load summary. From the start of the Montana-Wyoming border to the end, we gained, around 10,000 kilograms per year of arsenic. Well, where did that additional kilograms per year of arsenic come from? Well, it came from the anthropogenic arsenic load, as we discussed before, but that only accounts for 2.5% of the arsenic that ends up at the Bighorn River. The other, a larger percentage, 14.3% of the load is actually from tributaries, but it's a non-anthropogenic load. The anthropogenic arsenic load is actually included in the anthropogenic arsenic load. There's another component that you have to look at, and that's unaccounted for load or error within the model. And the error was 3.2%, which is great. Anything less than 5% is, we consider, a pretty well-balanced model. And then we end up with 100% at the Bighorn River. So the takeaway from all this is that the total non-anthropogenic arsenic from the Montana-Wyoming border to the confluence of the Bighorn River is 94.3%. And so, you're looking at quite a bit of non-anthropogenic arsenic in the Yellowstone River. Okay, so moving on, with all that arsenic in the Yellowstone River, and we're just using the non-anthropogenic arsenic, we can calculate the NASS, or the non-anthropogenic standard. Okay, so this is another process that we developed in the Yellowstone model, or in the Madison River model. And once you have a demonstration of non-anthropogenic, which we just went through, we look at any existing or potential discharges on each segment of the Yellowstone River. So we ask the question, are there any existing or potential discharges on the segment of the Yellowstone River? And there was one segment 3, did not have any existing or potential discharges. So we would just default right to the annual criteria. Now, what I mean by the annual criteria, it is the median, basically the median condition of that segment for all 12 months out of the year. So we use all 12 months of data. And the alternative would be a criteria based on the low flow months. So you're just using the 9 months out of the year that's the low flow condition. So you're averaging the 9 months versus using the whole year. So the annual criteria would be more of a conservative criteria. Then we move on to the 7Q, then we look at the 7Q10. It's the 7Q10 greater than 0. For all of the Yellowstone River, the 7Q10 is greater than 0. And so moving on, and then you conduct the dilution test. Now, dilution test tells you if the flow of the dischargers is significant enough to change the median arsenic condition. And how we determine that significance is we call it the 1% significance. So if the flow of the discharges is greater than 1% of the low flow condition of the Yellowstone River at that point, it's considered significant. And if that's the case, then we default to the more conservative annual criteria. However, if it's not significant, it's not a large volume of flow, we can move on to the seasonality test. And if there is seasonality, and I'll show you an example of this shortly, so it'll become a little more clear, then we can default to a low flow criteria based on the 9 months, because since the flow is not very significant and there's not a large volume of water going into the Yellowstone River, the possibility of changing the median flow condition is quite limited, and so therefore a criteria based on just the 9 months of low flow will be given. Now, if there isn't seasonality, then we just default to the annual criteria. Okay, so the dilution test, first we start by looking at all the permitted discharges on each segment, and I divided each permitted discharge, and you can see the hydrologic segment that each permitted discharge discharges to. Again, as I told you, segment 3 does not have any permitted discharges, and segment 5 actually has 4. And then so you would add all 5 discharges together. So this is so for segment 5, there'll be quite a bit of volume of discharge. And let's move on to the next slide, and I'll show you the dilution test results. So for segments 1, 2, 3, 4, and 5, again, 3, there were no discharges. So 0 divided by the 7Q10 is still 0. So we default to the more conservative annual criteria based off of the median from the 12 months. And for segments 1, 2, and 4, the flow of the discharges were not considered significant, or they were less than 1%. And so we can move on to the seasonality test to determine whether we can allot a annual criteria based on low flow. And for segment 5, because the discharge volume was so great on all, because we had to add all 5 discharges together, is greater than 1%, and so that for that segment, we would default to the annual criteria. Okay, so to determine seasonality, you have to first develop a flow duration hydrograph, and we require a minimum of 5 years of data. We actually use 20 years of data because we use USGS stations. And then you develop a hydrograph and find the points of inflection for the high and low flow periods. And I'll show you an example of that. It'll become a little more clear. And then you conduct a statistical test to determine if there is a significant difference between the concentrations of the high flow versus low flow periods. Okay, so this is an example of the hydrograph for segment 1 at Corin Springs. And what we did is you take the average of your data, so the average of all January 1st. So this is a 20-year average of, if you look at 1 here, of all January 1st throughout the 20 years, and then so forth. And then you look at where's the high flow period and the low flow period. And you can see there's a very distinct high flow period. That's where the hydrograph shoots up and then back down. And the dates that coincide with that is April 21st to August 10th. We round to the nearest month. So we determined a high flow period from May 1st to January 31st. So May, June, July will be the high flow months, and the other 9 months would be the low flow period. Okay, and then we plug the concentrations for those 9 months and those 3 months. So the 9 months of high or low flow and then the 3 months of high flow, and determine whether there actually is a statistical difference between the high flow months versus the low flow months. And of course, there was seasonality. It did pass the test, and therefore we can move on to selecting a NASS that has the annual standard based on the low flow months. Okay, and this is what it looks like. This is the first segment, and these are the median non-anthropogenic concentrations for each month out of the year. Those in red are the low flow months, and those in blue are the high flow months. And we're only going to take the median of the red months, or the 9 months that are the low flow months. And you can see just by these numbers that there is quite the difference in concentration between the high flow and low flow months, even without performing a statistical test. But the median of the low flow months turns out to be 32. So the NASS for this segment 1 would then be 32 micrograms per liter. Okay, so we did histograms, seasonality tests for segments 2 and 4 as well, and their hydrographs looked quite similar, and seasonality was the result. So we were able to do an annual standard based on the low flow months for segments 2 and 4. And so that number was 24 for segment 2 and 14 for segment 4. As we said, for segment 3, there wasn't any discharges, so we just defaulted to a standard of 16 based on all 12 months. And for segment number 5, Clark Fork of the Yellowstone River to the Bighorn River, which it does include the Billings area, we didn't do seasonality because we didn't do the seasonality test because it didn't pass the dilution test. It was the flow was significant, and a NASS was not selected. And the reason a NASS was not selected is because the median concentration for that segment was 10, and the current human health standard for all of Montana for arsenic is 10, and so a NASS is not necessary for the last segment, and the standard on record, the human health standard on record, will remain the same for that segment. So it's only the first 4 segments where a NASS would be applicable. Okay, and this is just showing it pictorially what that looks like. And so you can see for the first segment, it would be 32, the second segment, 24, third, 16, fourth, 14, and then after the confluence with the Clark Fork of Yellowstone, the human health standard would apply to 10. Another thing to note is that the frequency and duration for these NASS criteria will be the average annual concentration not to exceed the actual NASS, and that will also apply for the human health standard as well. And I'll talk about that a little more in the conclusions. Okay, so in conclusion, 94.3% of the arsenic in the Yellowstone River at the confluence of the Bighorn River is in fact non-anthropogenic, as I did show you in the DOM. These results are subject to change, and it is still undergoing internal review as well as external review and finalization. The frequency and duration for arsenic will be changed for all of Montana. As I told you, it will be the average annual concentration not to exceed the criteria. And the DON and the NASS documentation will be completed and released for external review in 2018, likely towards the end of 2018. And if you have any questions, you can contact the Water Quality Standards section in the Water Quality Planning Bureau, and you can use the number and the email address on this slide. And I thank you, and have a great day.